Hi everyone, in this video I'm going to be building on this simple linear regression in my previous video to a multiple linear regression and prediction using Python scikit-learn. Here I'll be using numeric for my response variable and both numeric and categorical for my feature variables. Previously I've asked ChatGPT how do I perform regression prediction using scikit-learn in Python. This time I'm prompting it a little differently where I specify the specific type of variables that I'll be using. So basically I asked, how do I perform regression prediction using scikit-learn in Python with a numeric response and both numeric and categorical features? So it gave me pretty elaborate response in a stepwise manner from the necessary models that I need to import, and then how do I prepare my data, as well as how do I split my data into train and testing sets. And now this is an important step this time around where it talks about how you pre-process your data, first using the StandardScaler to normalize your numeric features, and the other one is to use OneHotEncoder to convert your categorical features into binary columns. It goes on to talk about how you can create a pipeline with steps to first pre-process your data and then fit your linear regression model. And then you can make prediction using your test variables, and lastly, how you can evaluate your model's performance. Let's go to our Jupyter Lab notebook. So I'm going to start by importing the necessary packages. And then I'm going to read in the one dataset I'm going to be using. It's the second one dataset that I've used in my prior videos. So let's read that in. Let's now take a look at the first 10 lines of the dataset. As you can see here, we have points and price, the two numeric variables that were used in the previous linear regression examples. In this video, we're going to be exploring two more variables which are categorical. One is country and the other one is the taster's name. I'd like to run a correlation analysis, and so let's run this real quick. And as we can see, the correlation between price and points is 0.416, and that's a moderately correlated relationship. Let's now check for missing values. So as we can see here, it lists out the variables with missing values. I'm going to go ahead and drop the rows that has the missing values in both country and price variables. So let's do that. And as you can see now, both price and country has no more missing values. Let's now look at our first categorical variable, which is the country variable. Using this valueCounts.index call, we will list out all the different countries within that variable. So let's run that real quick. So we have quite a fair bit. So let's count how many there are. There are a total of 42 countries. And let's then calculate how many values in each country. For the country variable, I'm interested to use the top 10 countries with the most value counts, and I'm going to define them here as country 2. Next, I'm going to get all the rows where country is in country 2. So let's run that, and let's check it. So there you are, we have the top 10 countries. Let's now take a look at the data set. So as we can see, we have about 100,000 rows of data. And let's now create another data set with only the variables that we're interested in, namely country, points, and price. So let's run that. And now let's quickly take a look at the new data set. So now we only have the 3 variables and all the rows that comes with it. Let's now create the response and feature variables. Using the .log call and supplying the column names, we save points and country variables in X country, and we save the price variable in Y. Let's have a look at X country. Right, so we have the 2 variables there. Now, the next thing I'd like to do is to reset the index. So I want to make this to start from 0 instead of 1. And so I'm going to use the reset index call. And if I go ahead and take a look at it again, so as you can see here, now the data set starts from index 0 And this is particularly important, especially later when we merge two data frames together. And this is to ensure that the two data frames are merged at the same index number. Let's now move on to some pre-processing work. And for that, we're going to be importing OneHotEncoder and StandardScaler from sklearn pre-processing. So let's run that real quick. Let's begin with converting the country variables to dummy variables. And for that, we'll be using the OneHotEncoder. And the first thing to do is to create an instance of OneHotEncoder. Let's run that. Using the instance, we'll transform the country variable into the binary variables and convert that into a data frame. So let's run that. And let's have a look at the first 10 lines of the result. So here it is. When you look at the result, you might ask which columns corresponds to which country. So when the labels are sorted alphabetically, the first, in this case Argentina, will be the baseline, which means it will contain all 0 values. And this will be followed by Australia, Austria, and so forth in alphabetical order. Now that we know the order of the country names, we can name the columns respectively. So let's run that. And let's quickly take a look at the result. So there you have it. We have successfully created binary variables for country. Now let's move on to normalizing the points variable. In normalizing a numeric variable, we subtract each observation by its mean and divide by the standard deviation. When the numeric variable is normalized, we are expressing the coefficient as the effect of one standard deviation change in x. So we will interpret a change in y measured for one standard deviation change in x. I had a question on why we should normalize numerical data. So I asked ChatGPT just that, and it gave me several reasons. So I've summarized the reasons here, and I'm going to pick a couple to talk about. First, it avoids bias. So some algorithm apparently gives more weight to variables with larger values and deem it as more important. Also, normalizing ensures compatibility with certain algorithms, so it ensures fair comparison and accurate results. Let's start by creating an instance of StandardScaler. And then we're going to transform our points variable and turning that into a data frame. And we'll name the column as points normalize. Let's now take a look at the results and the first 10 rows of the data frame. So there you go. Now that we have pre-processed our numerical and categorical variables, let's merge them together. And let's now take a look at the first 10 lines. We can now start training our model and building it. So first we import train test split and linear regression. Let's do that. And let's split the data to testing set and training set. And we'll print the shape to have a look. So basically we have 30% of our data as the testing data. Let's now fit linear regression to our training sets. To evaluate our performance, we use model.coef_ to get the coefficient and model.intercept_ to get the intercept. I've previously ran this model without the numerical variable being normalized. What I've got is a coefficient around 5.6, and that is the change effect of a 1 unit change in x. So as you can see now, with the numeric variable being normalized, our coefficient is 17.3. So that is the effect of one standard deviation change in points. Using our model, we predict y based on x-test dataset. To further evaluate the model's performance, I imported mean squared error and R2 score from sklearn metrics. And then I calculated R squared and RMSE using the formulas. So R squared measures how irregularity in the dependent variable the model can explain. Bigger value shows a better fit between prediction and the actual value. So the R squared value is calculated to be 0.187, which is not too far off from the R squared obtained with just points as the feature variable. The next metric is RMSE, which is root mean square error, and it's the measure of the typical size of the residuals and how much predictions are typically wrong. So here it is calculated to be around 37. That means the difference between the predicted value of price and actual price is typically around $37. The second categorical variable that I'm interested in is the taster's name variable, and I've listed all the tasters here, and there are 19 of them. Here are all the value counts for each taster, and I'm going to define taster 2 as the top 10 tasters according to the value counts. So pretty much I did the same thing, isolating rows of data containing tasters in taster 2. I've also created both response and feature variables by isolating points and taster name in X and price in Y. Using our preprocessing method, OneHotEncoder and StandardScaler, I converted the taster's name variable to binary variables. Using StandardScaler, I've also normalized the points numeric variable. Here we have in one data frame the normalized points numeric variable and also the converted taster name variable to binary variables. I split the dataset into 70% training and 30% testing. After fitting linear regression on the training set, I got this as the coefficient and the intercept as this one. I then predict Y using the model on X test dataset. Finally, computing for the R-squared and RMSE values, I got a value of 0.154 for the R-squared and 45 for the RMSE. So the R-squared value calculated this time, 0.154, is a little bit lower compared to the other two values that we've got in our previous two models. As for the RMSE, the value of 45 deviates quite a bit as well from the value of 37 that I've got in the other two models. So I'm going to compare side by side the three different models. So this one with just the price as the only variable, R-squared is 0.211 and the RMS is 37. This one with points and country as the variables, we have R-squared of 0.187 and RMSE of 37. And lastly, for the one that we just calculated for points and taster's name, the R-squared is 0.154 and the RMSE is 45. So it seems like adding taster's name brings down the goodness of fit quite a bit compared to adding countries. Adding country versus not adding country didn't really bring down the R-squared by a whole lot while maintaining the RMSE at around 37. So I went ahead and calculate the adjusted R-squared values for both models that contain the additional country variables and taster's name variables. Unlike R-squared, adjusted R-squared pays a price for the inclusion of unnecessary variables in the model, and adjusted R-squared only increases when independent variable is significant and affects the dependent variables. What I've got from the calculation is that the adjusted R-squared is pretty similar to the R-squared value. So this one is for the points and country variables model, and as you can see, they're pretty similar. And over here, with the points and taster's name model, we can see that the adjusted R-squared is also pretty similar to the R-squared. As you can see in all three models, the R-squared values are pretty low. So what I'd like to do in my next video is to investigate combining points with taster's name and country to see if that is a better model. So I'll see you there. Bye for now.